Okay, so let's get started. We will finish up the probability unit that we've been talking about in the last couple of lectures, and then we'll move on to the next topic. Okay, so basically, we looked at this medical testing example where you have a condition that is, relatively rare, right? So we have a condition that is relatively rare, and we also have a test that is pretty accurate, right? So it's got 5% and 2% errors, 5% in terms of uh, saying that somebody who doesn't have the condition is actually sick, and the 2%, if you look at the other way, that is somebody who actually has uh, the disease, but the test says uh, this person is okay, right? So if we work through our conditional probability equations, what we end up with is the surprising result that even though the test is 95% accurate or better, right? Uh, Even then, a positive test means a relatively low probability of having the disease, right? So even though the test comes out positive, there's a very high probability that you don't have what uh, you don't have the underlying condition, right? So this happens because you have two things going on here. One is that uh, you know you have a very rare condition, right? So the sickness itself is very rare. And so, uh, in fact, the sickness is more rare than the rate of errors in the test, right? The test has an error rate between 2% and 5%, whereas the rate of sickness is only 1%, right? Because of that, uh, so what ends up happening is that the vast majority of the people who are tested, right, 99% of them are really not sick. And as a result, even a relatively small false positive rate of 5%, because such a vast majority of the people who are being tested are not sick, you end up producing a relatively high score over here, right? And as a result, when you add the false positives that you get here with the true positives that you get here, it is the false positives that dominate because they are about 5 times as much as the true positives, right? So this is a true positive because you are sick and the test comes out positive. So that is a true positive. You are not sick here and then the test comes out positive. So these are your false positives, right? So when a test comes positive, you know that either you are here or over there, right? But because false positives ends up being 5 times larger than the true positives, the net result is that even though the test says you're sick, the actual likelihood of you being sick is only like 1/6. Okay. So this is something that you need to be aware of whenever you have uh, uh, these sort of situations where you have two rare uh, events, and then when you look at the combinations of these events, then you can get some unintuitive results, and that's sort of what you need to watch out for. And this is one of the reasons why many times in medical testing, uh, any kind of testing that's done on a routine basis to large populations is going to have a very high effective false positive rate like this, right? So it's basically 85% false positives, right? So 16% is true, 85% is false. So I don't know how many of you follow changes in recommendations for what people should be routinely screened for. And this is one of the reasons why those recommendations change. And so, for instance, a few years ago, the recommendations for routine screening of breast cancer cases, the recommendations were changed because people said, well, there are the false positives are too high for younger women, and therefore the net benefit to the society is increased if you don't do as much testing for some of the younger women, right? And similar changes have been made to many other conditions that people used to be routinely screened for. Okay, so interesting. I guess the semester, it's getting late in the semester, and so we've lost some people in the class. Any questions? So I'm going to go on to the next unit. Any questions about this unit or the homework or the test? Well, the test is not for another 2 weeks, so it's not something to worry too much about yet. Okay, good. Oh yeah, that's right. People are probably voting. That's good. Better reason to miss class than any other reason, right? Okay, very good. So let's go back to, let's go on to the next unit. Okay, so now we started the course with proofs, and we are back to proofs again, right? So we will revisit proofs, in particular, 2 proof techniques which we did not discuss before. And that will be the roughly the material that's included for your next midterm, right? So we start from summations, counting, probability, and induction proofs, right? So that's the material that will be included for the midterm that's coming up in 2 weeks. So we start with what is called a well-ordering principle. And this principle looks deceptively simple. Right? Every non-empty set of non-negative integers, right, has a smallest element. So for instance, the set of natural numbers or any subset of natural numbers has a smallest element. Okay. Now that may not seem profound, so there are 2 things that you need to keep in mind. The most important thing is that this note applies to infinite sets, right? So it's fairly obvious that every finite set has a minimum element, right? Because you can just enumerate, you can just list the elements one by one, and then you'll go through all of the elements in finite amount of time, and in that process, you can identify what is the smallest one, right? So we will. So can a few more of you turn on the camera? Okay, good. So so it applies to infinite sets, and of course the set must be non-empty. right? So an empty set obviously does not have a minimum element, right? So the principle seems obvious, but we lack any way to prove it. Okay, so we will take it as an axiom, right? So that's something that we believe to be true, and we will you know assume that it is in fact true. Okay, so now and we have used this principle many times. So for instance, when we prove that square root 2 is irrational, uh, we would say, okay, then it can be expressed as p divided by q, and uh, we make the assumption that p and q are as small as they can be, right? And then we say it the other way. We say that is by saying that they don't have a common divisor. Okay. Similarly, when we said there is infinitely many primes, uh, once again we relied on this well ordering principle somehow, um, but we didn't specifically point out, and the reason is that uh, I wanted you to understand proofs to some extent without getting caught up in some axioms that may seem confusing at best, like the well ordering principle, because it seems, if you look at this axiom for the first time, you'll all, you just can't wrap your head around it. Why is it important to say something like this? Because if we start doubting whether this is true, then where would we stop, right? Um, so sometimes it's better not to, learn axioms like that, at least early on in the course. And then hopefully by now you have seen enough formal material that you can look at something like this and not be too disturbed, right? And so that's why I'm bringing it up now, and we will see how to use it in various proofs. Okay, so these well ordering proofs, right, they are basically proof by contradiction, right? So the primary technique we have used repeatedly in our proof so far is proof by contradiction, right? So we assume that something is true, and then we later on show that, well, it's not true, and therefore. So, but most of the time, the proof by contradiction needs to be combined with this well ordering principle in order to prove sort of general properties, and we will see that through examples in this unit. Okay, so these well ordering proofs have a specific template which I think you will find useful when you are asked to write proofs. The fact that there is a fixed structure makes it somewhat easier to approach the proof problem. So the first step is, you are trying to prove a theorem, right? Such as, well, the sum of the first n numbers is given by n times n plus 1 by 2, right? It's something that we have proved like 10 times so far, right? So that's a kind of a theorem that you may want to prove. And the way you use a well ordering proof is to start by assuming that, start by saying that let there be some set of examples, some values of n, such that this formula does not tell you the sum up to n, right? So that is called the set of counterexamples, right? So you have a theorem, and there are a set of counterexamples to the theorem. Okay, and of course, if the counterexample set is already empty, that means, well, the theorem is true, right? So there's nothing to prove. So the only time you will have to prove something is when this set of counterexamples is non-empty. Okay, so then you would invoke the well ordering principle to say that, okay, if C has elements, then it must have a minimum element. Okay, and we will call this minimum element as n. Okay, and now using n, we will establish a contradiction. Okay, what is a contradiction that we will establish? We will show that there exists some other m, right, that's less than n, but it should also be included in the counterexample set. Okay, so that would be a contradiction because you already said n is the smallest element, right? So now if you could say that, hey, there is some other smaller element than n in C, that's a contradiction, which means that, well, there is no smallest element of C, right? Because this is what you assumed, and then you showed another smaller element, which means that there does not exist a smallest element in C. And then you can say from the well-ordering principle, the only way you may not have the smallest element is because it's empty. Okay, so you would conclude that C must be empty, which means that there are no counterexamples to the theorem. Okay, so let us go through an example to see how this works. So we have the same old theorem that we want to prove, right? Summation up to n is given by n times n plus 1 divided by 2. Okay, so now the counterexamples is the set of numbers such that they don't obey this formula, right? So we're going to say the set of counterexamples C consists of numbers such that this, so we will call this as the predicate P of K, right? So we're going to have this identity, and we are going to call this identity as P of K, right? And P of K is basically the theorem that you want to prove, right? So a counterexample would be one for which P of K does not hold, right? So, and the set of counterexamples would be all K such that P of K does not hold. Okay, so now that you have set up the set of counterexamples, your second step is always that you're going to assume that C is non-empty, right? Again, let's look at the template. The first step is to define the counterexamples. The second step is to assume that C is non-empty. Okay, so that's what we do. Assume that C is non-empty. Okay, so then the third step, you invoke WOP to say that there exists a minimum element R belongs to C. Okay, now this is only because C consists of positive numbers, right? Remember that well-ordering principle right? So every non-empty set of non-negative integers has the smallest element, right? Because obviously, if you take the set of integers, there is no smallest element, right? Because any negative number you can find, well, there is something less than that negative number, right? So there is no way to find a minimum element if there are an infinite number of negative numbers, right? So this is why WOP holds for sets containing integers and sets containing non-negative integers, right? So this is something that you should pay attention to, okay? So here we start by defining C to include only elements from N, right? So only elements in N, some of those elements are in C. Therefore, every element in C is already a natural number, and therefore the well-ordering principle is applicable. Okay. So now by applying the well-ordering principle, we say, hey, there must be some element R that is the minimum element in C. And then we're going to say that since R belongs to C, P of R must be false, right? Because that's how we defined the set of counterexamples. The set of counterexamples includes numbers such that P of K is false. So P of R is false, which means that this quantity is not equal to this quantity, correct? So we say that these two are not equal. Then we are going to do some arithmetic manipulation, and then we are going to show that. So after that arithmetic manipulation, we'll show that it's also the case okay. So essentially what we will do is we will subtract R from either side of this equation, okay? And then we will end up with something like this, right? And then this is nothing but P of R minus 1, right? Because if you change this inequality into equality, then it will be P of R minus 1. And since it is an inequality, then what it is saying is that P of R minus 1 does not hold. Okay. So what that means is that R minus 1 is also a counterexample. So R minus 1 should have been in C, right? But then we said R is the smallest element in C. So obviously R minus 1 couldn't possibly be in C, which is a contradiction, and therefore we can conclude that C must be empty. Okay, so let's go through these steps in more detail. So P of R is false, so you have this, right? So now let's say subtract R from both sides. Okay, so then if we remove R, then this sequence will end at R minus 1, right? So if you just remove R on the left-hand side. And then we also subtract R from the right-hand side, right? So we subtract, so we have an inequality, X not equal to Y. So remember that if X is not equal to Y, that implies that X minus right? If two things are not equal, then you subtract something from the same quantity from both sides, the result will also be not equal, right? So that's why we start from this, we subtract R from two sides, then we end up with this inequality. And now we simplify this, R times R plus 1 minus 2. We multiply R times R is R square, R times 1 is R, right? And then when we bring this R to the numerator over here, that's going to become 2R, right? Because there is a 2 in the denominator here. So when we bring this R in the numerator, it's going to become 2R. So we have this, and then we can cancel those two, and you will end up with R square minus R divided by 2, which you can factorize by pulling out 1R. So you'll get R minus 1 times R divided by 2. Okay, so that's what you get from this. And so in other words, this quantity up to R minus 1 is not equal to this quantity, right? Because we started with this not equal to this, and we showed that this is nothing but that quantity, and therefore we can replace this quantity with this quantity, right, in the original inequality. So we are able to say 1 to R minus 1, the summation is not equal to R minus 1 times R divided by 2. And then now we match it with the structure of P, and then we see that, okay, this is saying nothing but not of P of R minus 1. And then once we say not of P of R minus 1, by definition of the counterexample set, R minus 1 must be in the set C. Okay, but then this this contradicts the assumption that R is the smallest element of C, and then pretty much. So this contradiction shows that C must be empty, right? Because if what this contradiction shows is that there is no minimum element in C, and by well ordering principle, you can conclude that if there is no minimum element, then the only possibility is that the set of counterexamples was already empty to begin with. Okay, so there is one little point that I didn't explain so far, and that is that we need to be a little bit careful when we take off R from the right end. Okay, because if let's say R was already 0, right? Then R minus 1 is not a natural number, right? So we need to be, when we do these things, like, okay, I'll remove R, you need to make sure that R is actually greater than 0, right? So that is the detail that we deal with there. We say that, okay, so this is possible because R is actually greater than 1, and therefore R minus 1 is also greater than or equal to 1. And that's why we can go through this, right? And so this, in fact, to show that R greater than 1, how do you show that R is greater than 1? Well, you show that P of 0 and P of 1 are already true. Okay, if you're able to show that, then 0 and 1 will not belong to the counterexample set. Correct? Because you can say that some elements do not belong to the counterexample set by specifically showing that the theorem holds for those values, right? So if you substitute n equal to 0 on the left-hand side, right? So by the way, a summation like this, okay, what it means is that there are only 0 elements here, and summation of 0 elements is always defined to be 0. Okay. Similarly, if you have a product and you have a product of 0 elements, what do you think that value will be? If you take a product of 0 elements.
0.
So the way to think about it is that when you add the next element, you should get the right result. So if you have a sum of 0 elements, so you get sum of 1 elements by adding 1 element to sum of 0 elements, right? So because 0 plus that element is equal to that element, therefore, by convention, the sum of 0 elements is 0. Okay, but if you apply the same logic to product, right? So then the number has to be 1, right? So the product of 0 elements is to be 1, because if you add one more element to the product, right, the result should be product of 0 terms multiplied by the last term that you added. So that'll work correctly if you define the product of 0 elements as 1. Okay, essentially it has to be the identity for that operation, right? So what is the identity element for 0? It is 0. I'm sorry, let me say that again. The identity element for the addition operation is 0. The identity element for multiplication operation is 1, right? So we are going to define the summation or product of 0 terms as the identity element for that operation. Okay, so anyway, this is sort of a side point, because I'm sure there will be instances when you're trying to prove things like this, you will encounter situations like this where the last element seems to be smaller than the first element, and you're left wondering what it means. And what it means is that this summation is going to be 0. Okay, so why did we get into this conversation? That's because we wanted to say that certain elements are not part of C. Okay, and you can prove that. You can say, for instance, 3 does not belong to C, because if I substitute n equal to 3 in this, I'll find that this equation actually holds for n equal to 3, right? And therefore, I know that 3 does not belong. 3 is not one of the counterexamples. Okay. So similarly, I can apply it to 0 and 1 and say that 0 and 1 do not belong to the set of counterexamples. And that's how I'll be able to say that any R that is in C is going to be greater than 1, because 0 and 1 are simply not in the counterexample set. I just checked, right? I checked whether 0 and 1 could be in the counterexample set, and I found out that no, they cannot be in the counterexample set. So they are not in the counterexample set. Therefore, R minus 1 is a well-defined natural number, because R is neither 0 nor 1. Okay. So this is pretty much the structure of all well-ordering proofs. You have a couple of examples that you have to solve in your upcoming homework, and it'll pretty much follow this this outline. It should not be particularly difficult. It's just I give you those examples so that you get some practice, because you obviously have to do it yourself in order to really understand how to do it. But otherwise, these types of proofs should be relatively straightforward. And one of the things that we will discuss today is how these well-ordering proofs are so closely related to induction proofs that we will talk about next. And this is another reason why I'm not going to go through several examples of well-ordering proofs, because the proofs pretty much look like induction proofs written in slightly different way. Okay. So before we wrap up this topic, I will, summarize something about sets other than the set of natural numbers. Okay. So well-ordering is not a property of just natural numbers. It can be applied to other sets. And here is the definition of well-ordering, right? So a set is well-ordered if every one of its non-empty subsets has a minimum element. Okay. So can you think of a set that has a minimum element, but there are subsets that don't have a minimum element? Okay, you can think of infinite sets, because obviously any finite set is going to behave in a much more expected way. It's only the infinite sets that are going to have somewhat unusual behavior. So thinking about infinite sets, can you think of an infinite set which has a minimum element, but some of its subsets don't have a minimum element?
You could like construct a set, say like 1 union with real numbers between 2 and 3.
So for instance, let's take this. Right? The set of real numbers between 1 and 2. Right? Now, if you subtract 1 from it, rather remove 1 from it, so you get a subset of this set, right? This interval of real numbers 1 to 2. So if you remove that 1, then what is the next minimum, right? It's undefined, right? Because if I say, no, it's 1.0001, obviously there is 1.0001 that's smaller, right? And then I can say 1.0001 that's smaller, right? So there's no way to stop, right? So no matter what element you give me, I can find something smaller than that, right? So so this is why we have this condition that every subset must have a minimum element in order for the well ordering principle to be applicable. Okay. So so well ordering principle is applicable to any well ordering set, well ordered set. Okay. So a couple of examples of well ordered sets. Okay, so this is an example where we already talked about a set having a minimum element, but it may not be well ordered because it has subsets that have no minimum element. Okay, so so to give a positive example of a well ordered set, you can take you can construct a well ordered set that contains negative elements, right? And if you take any set of integers with a minimum element, right, then that is going to satisfy, because if you if let's say the minimum element was minus 100, right, because it is integers, so you can enumerate the set of integers, and therefore you can arrange this set in increasing order from the minimum element, right? So if I remove the minimum element from the set, then the next element in that enumeration will be the next minimum, right? So therefore, any set, even if it has negative elements, is well ordered, provided the set has a minimum element to start with, right? So once you have a set with negative elements that has a minimum element, then every subset will continue to have a minimum element, unlike the example of the real numbers that we gave, right? So if you have a set of integers, then you will be able to find subsets that continue to have this minimum element property. Okay. Similarly, if you want to have a set of real numbers with that's well ordered set, well, the only thing you can do is if it is a finite set, right? If any finite set, of course, is going to satisfy a well ordered property, right? Because you can always go through all the elements and find the minimum, right? And if you take a subset, once again, you can go through all the elements in the subset and find what is the minimum. So okay, so this is sort of the technical definition of well-ordered sets, but by and large, we will be applying well ordering to integers. Okay. So we proved that. So it was one of the first few topics when we proved that there are infinitely many primes. Okay, so it's probably in the first 1, 2, or 3 chapters in the textbook. Okay, and then it's one of the first topics that we covered in the class. So now let's move on to the next topic, which is mathematical induction. Right, as I said before, so the mathematical induction and proof by contradiction are essentially the same proofs. Okay, so in induction, what you do is that you start from 0 and then say, you first show that something is true for element 0, right? So you establish P of 0. And then you say that if P of n is true, then P of n plus 1 is true, right? So you're going to start by proving P of 0. Then you're going to prove this general property. That is, whenever P of n is true, P of n plus 1 is true, right? And once you prove that general property, then you can start from P of 0, apply this property to derive P of 1, right? And then again, you can apply this property once more to get P of 2, P of 3, and so on, right? So which means that once I prove this, and then once I prove this, then I can go up this chain as many times as I want, and still P will be true, right? So this is a very simple and constructive way of proving a property for all integers, right? So mathematical induction starts from 0 and goes up, okay? Whereas well-ordering proofs start from some random place here, and then they try to come down, right? So in the example that we just did, we said, okay, let's assume that P of R is not true. Then we said, okay, not of P of R minus 1, right? This is what we did. So in other words, here in the induction proof, we build bottom up, and in well-ordering proofs, we kind of break top down, right? We kind of say, oh, if this does not work, then this does not work, and this does not work, and this does not work, right? So essentially we say, hey, suppose you say P of not P of R, then not P of R minus 1, and so on. So essentially P does not hold for anything, okay? So this is why well-ordering proofs are like a mirror reflection of induction proofs, okay? So we'll come back to this point later on. So let's now focus on just induction proofs, right? So once again, there are two things we do. We prove what is called the base case, okay? That P of 0 is true. Sometimes 0 is not the base case. It might be 1, it might be 2. Most of the time it is 0, right? But sometimes it can be some other numbers, but generally a very small number, right? So you start, that is your foundation, right? So this is the foundation for your building. And then this is how you build each floor of your building, right? So you say, okay, I built the nth floor. Now I know I can build the n plus 1th floor, right? So that's how you start from 0. You build the first floor, second floor, third floor, and you know that all those floors are, none of them is going to collapse because there is a floor below. And once you have constructed the nth floor, you know how to construct the n plus 1th floor on top of it, right? So that's kind of a way to think about how induction proofs work, okay? And here is an inference rule that captures how the induction works. So you prove that P of 0, and then you also prove that for all n, P of n implies P of n plus 1. Then you can conclude that P of m holds for every n, okay? Because of this constructive process by which we are able to prove P is true for each and every value of n, okay? Any questions so far? It's too simple, right? Just make it more difficult, and then there'll be more reaction. Now, this is induction. Among all the proofs, induction is definitely the most intuitive, because you can sort of really, I think, understand why, you can sort of believe that this is actually a proof, because it as I mentioned several times with proof by contradiction, you need to get really familiar with the technique to integrate it into in your mind, and sort of internalize why the proof really works. But I think it's much easier to internalize induction because it's something that I think most people are able to, uh, relate to. How does this induction principle work? And it's a principle that seems to be, easy to understand and easy to believe. Okay, so just like well ordering proofs, there is a 5-step process for establishing induction proofs, right? So the first step is you would say, I'm going to use induction, right? And in general, when you do induction proof, the induction is on some quantity, okay? Some quantity that is an integer, okay? But most of the example proofs that we will do will be proofs involving properties of numbers. Therefore, you will simply do induction on the number that is involved, okay? But there can be some situations where the proof is not based on some number. So for instance, you might prove some properties of strings, right? So if you want to prove some property of a string or prove some properties of strings, then there is no number there, right? So you need to say, okay, what is the induction going to be on? And typically the induction might be on the length of the string, okay? So your induction may not be on always on so induction will always be on a number, but the number you may not always be working with the properties of numbers, right? You may be working with properties of other things like strings. And then you have to say, okay, I'm going to do induction on this property of this object, okay? So, but again, that complication, we don't have to worry about it for now, for quite some time. So we are only going to talk about properties of integers for quite some time, okay? Um, so the second step is you define induction hypothesis, which is this predicate P of n, okay? So P of n will typically be just the property that you are trying to prove, right? So as things get advanced, there may be situations where the induction hypothesis may be somewhat different from the property that you want to prove. But once again, you're probably not going to encounter those situations. And for in most cases, right, in 9 out of 10 cases that you'll encounter, your induction hypothesis is going to be exactly the same as the property that you want to prove, okay? Then you establish the base case, which is showing that P of 0 is true. As I said, there will be cases where instead of P of 0, you may be proving P of 1, okay? But still it is called a base case, right? It's your basement or foundation, okay? Then the most important step is this induction step, okay? So where you go from P of n to P of n plus 1, right? This is similar to the establishing contradiction step of well ordering proofs, where you're going to say, well, if P of n plus 1 doesn't hold, then P of n does not hold, right? So that's the way you would do a well ordering proof. Here, you start from P of n and say that P of n plus 1 holds. And then you're pretty much done at this point, right? So once you're shown this fourth step, then you sort of have to remind the reader that, okay, you are using induction and therefore this concludes the proof. Okay, so let's take the same summation example for the 12th time and go through how this proof works, right? So we want to prove that summation of I equal to 1 to n, I equals n times, right? So this is what we want to show. So the first step, we say that proof is by induction on n, and then we write down the induction hypothesis, which is basically the condition that you are trying to prove. So you define Pn to be this equality, right? Summation I equal to 1 to n of I equals n times n plus 1 by 2. Okay. Then we identify the base case, right? So here is a case where the base case of 1 seems to make sense, right? So because you start from 1 plus 2 plus, therefore the base case of n equal to 1 seems to be more natural. So we take that base case and then we calculate I equal to 1 to 1 of I is just 1, and then we verify that the n into n plus 1 by 2 in this case will become 1 times 1 plus 1 divided by 2, and that is just 1, and therefore you can say, hey, P of 1 holds. Then you do the induction step, which is sort of pretty much all of your real proof, right? So these are sort of mechanical steps, right? So you can write down the induction hypothesis, you can establish the base case. So these are mechanical steps. The only step where you may need to do something slightly intelligent is the induction step. Okay. So typically the proofs that you're going to deal with are going to be proofs involving integers, and therefore you'll be doing some algebraic simplification to establish to show that P of n implies P of n plus 1. You will largely be using some kind of algebra, right? So let's say what this is. So we add one more element, right? So remember that this is nothing but sigma I equal to 1 to n times I plus, right? So this is what this quantity represents. Okay. So what we are doing is we are adding n plus 1 on the left-hand side of P, right? So we are adding n plus 1 on the left-hand side of P. Therefore, we should add n plus 1 on the right-hand side of P, right? So that's what we have done here, right? So we start with P of n, right? And then we add n plus 1 on both sides of P of n, okay? And now we do our, so we take n plus 1 is a common factor between these two terms. So we bring out n plus 1, and then inside this is n plus 2, n by divided by 2, and then this produces 1. So you get n plus 1 times n plus 2. And then if we do complete the addition, then n by 2 plus 1 will end up being n plus 2 divided by 2. So then you whole thing becomes n plus 1 times n plus 2 by 2, right? So we have sigma I equal to 1 to n plus 1 of I, and n plus 1 times n plus 2 divided by 2. So you can see that if this is equal to this, then that is nothing but the statement of P of n plus 1, right? So if you take P of n and if you put n plus 1 in the P predicate, then you will end up with this on the left-hand side and this on the right-hand side. Therefore, we have established P of n plus 1. So now we invoke induction to say, hey, P of k holds for all k. Okay. Any questions? So there is let's see whether this works. So there is I have a link on this page, right? Which is to a set of sample induction proofs, right? And there are like 15 or so examples in this write-up. I think it's from Illinois. It doesn't matter where it is from, but these are good, well-written proof examples meant to show you how to write proofs, right? It is not meant to sort of, show you here is a, that certain things are true, but instead it's basically to give you practice for how to prove things. So, and it's also not very long. So let's see how many are there. See, it's 7 pages and 14 problems, right? So it's a nice set of examples that you can look at. Okay, so let's go back to. So this is the URL. So you can just click on that and look at that. And before you do your homework, right? Do look at these examples, because it's good to look at more than one example before you start writing your proof. Okay, so now that you're all experts in induction proofs, why don't you look at this proof and tell me what's wrong with it, right? I've proved that all horses have the same color, right? So how do I do that? Well, base case, well, the base case is for a single horse, right? Of course, a single horse has one color, right? So, right? There are no two horses for me to compare and say that one horse just, they don't have the same color. Now, induction hypothesis is going to be that all horses with, that I know that it is true for P of n, right? So I'm going to say that my P of n is going to say that all horses with, all sets of horses with n horses, right? Or rather, any group of n horses has the same color, right? So this is going to be my induction hypothesis, right? Now, remember, all I need to prove is that if P of n is true, then I need to prove P of n plus 1, right? So this is how I'm going to do this, right? So let's say I take n plus 1 horses, right? So because I know P of n holds, I know that all of these horses have the same color, right? Same way I can look at H2 through Hn plus 1 and say that all of them have the same color, right? So if all of these have the same color and all of these have the same color, well, obviously everybody should have the same color, right? Well, of course, you know that this theorem is not true. So where is the mistake? Greg?
I think the mistake lies in the induction hypothesis, where they say that all sets of horses with n or fewer horses have the same color, but really it should be all sets of horses from 1 to n, from position 1 to position n, or something like that.
No, because this, I'm just pointing out a subset, right? This is a subset of n horses.
Mhm.
And therefore, by induction hypothesis, I can say that all of them must have the same color.
Right, but I thought that the induction hypothesis itself might have been incorrect.
Just says, okay, so let me, okay, I will rewrite it to say all sets of okay. I can, if this wording is clearer, then I will use this wording. All sets of n horses have the same color, right? Or I would say, anybody else? Well, obviously there's a mistake, right? So it's not like Brian.
how do you know that the induction hypothesis is true, that all groups of n horses have the same color?
Well, that's the whole point of induction proofs, right? So remember, we are not, this is how we build, right? We go from 0 and then we build, right? So 0 is the foundation. So we are able to make the assumption about P of n because we have climbed up to the nth floor, right? We have built up to the nth floor already, right? And all we need to show is that if we know how to build up to n floors, then we can build the next floor, right? That's all we need to show.
Maybe you can't start the induction because like you
No,
start
no,
by
I
saying,
already started it, right? So because P of 0, right?
yeah.
Or P of 1, right? I already, all groups of 1 horses, of course, have the same color, right? So there is obviously nothing wrong with induction itself, right? Because well, we wouldn't be studying induction if there is something wrong with induction. So Owen. Yeah, go ahead.
In the induction step, you have to prove that P of n implies P of n plus 1 for all values of n, but the only reason it works here is because there's overlap between the two of them, which for n equals 2 wouldn't be the case.
So do you understand what's going on? So this is called sleight of hand, right? So I'm operating like a magician, trying to distract you and showing you some irrelevant structure that actually does not exist. Okay, and the structure that does not exist is that there is this implicit assumption that this set H1 through Hn has at least 2 elements, right? Because what I'm appealing to by when I say, okay, if this has same color and this has same color, then everybody must have the same color. What I'm assuming is that there is a Hn that is common between these two groups, right? That is what is making sure that if these n have the same color and these n have the same color, then all of them have the same color because there is a common element between this set and this set, right? And that is true only if n is greater than 1, right? So when n equals 1, there is no common element because if n equal to 1, then I have H1, H2, right? Those are the only 2 horses. Then let me draw the picture, right? Well, this has the same color. This has the same color. But obviously from that, you cannot conclude that H1 and H2 have the same color, right? So what I have done is by using imprecise notation, I have made an inference that's incorrect, right? The incorrect inference that I've made is that I have, just because I wrote H1 through Hn, I implicitly assumed that n is greater than 1, right? And that's not true. So essentially what happens is that P of 1 is definitely true, but as this example shows, I will not be able to go from P of 1 to P of 2, right? What this part shows is that if somehow I manage to build the second floor, then I can build everything else. But I really cannot build the second floor because the induction step has incorrect reasoning that does not work when n equals 1. So you are not able to go from P of 1 to P of 2. Any questions? So this is something that you should always watch out for, because this kind of notation is a bit dangerous because sometimes the notation sort of misleads us into thinking that there are at least so many elements when in fact there may not be that many. Yeah, I guess somebody else answered it on the chat, but I guess I was too late, too slow to notice it. Okay, good. So so there is a variation of induction called strong induction, and the difference between simple induction and strong induction is that in simple induction, we assume P of n, and then we prove P of n plus 1. Right? In strong induction, we assume Pn minus 1, Pn minus 2, and so on. Right? So we often end up assuming, P of I for 0 less than or equal to I less than or equal to n. Right? So this will be our induction hypothesis. Right? So essentially what we are saying is that we are not going to assume that we have built just the nth floor. We are going to assume that we have built the foundation, the first floor, second floor, third floor, all the way up to nth floor, right? All of these floors exist, right? And then we're going to build the n plus 1th floor in the building, right? So that's what strong induction says, okay? So there are proofs where you need this stronger assumption that all the floors below you exist, right? So, think of, let's say, a fancy building where somehow some of the supports from the n plus 1th floor, go to the n minus 1th floor rather than the nth floor, right? So then, of course, you need to know that the n minus 1th floor also exists. So, by making a stronger assumption, you may be able to prove things more easily. And when we write down the inference rule, what it says that P holds for the base case B, okay, and that it holds for all values less than or equal to n. And if you assume that, by assuming that P holds for all values less than or equal to n, if you can prove that P of n plus 1 is true, then once again you can conclude that P holds for all values of n, right? For all natural numbers. Okay, so somehow there is, while it is useful to know that you're using strong induction versus weak induction, there is really no big difference in terms of, it's not that one type of proof is better than others, better than the other, or that one type of proof is, preferable over the other. There is no such thing, right? So there are going to be situations where simple induction would work, and there are going to be situations where you need the stronger assumption of strong induction, right? And so it's useful to be aware of that, but don't worry too much, right? So the distinction is not such, is not so fundamental. There is, in fact, a straightforward way to take a simple induction proof and convert it into strong induction, or a strong induction proof and convert it into using simple induction. Okay, so the distinction is not that critical, but it is useful to know. So let's take an example, another example, right? So there's a stacking game, right? So you begin with a stack of n chips, right? So let's say, 2, 3, 4, 5, 6, let's say 7 chips, right? And then each move of the game, you split the one stack into 2. Okay, so let's say this, you split into 1, 2, 3, 4, and 1, 2, 3. Okay, and you split the stack into 2, and you get AB points. So this move will give you 12 points because A is 4, B is 3. So you start with a stack of A plus B chips and you break it into 2. So we are going to, A simply refers to the height of the first stack, and B is the size of the second stack. Okay. And now maybe you can break the 4 stack into 2. Right. So you took a 4 and made it into 2 times 2. So you're going to get 4 points for this. So do you understand how the game works? Right. So, and then, maybe you split this one now. And so you have right. So now you took a stack with 3 chips and made it into 2 and 1. So the points you're going to get is 2 times 1. So you're going to get 2. And then you can see that, well, from here on, I'm going to have right. So I took this 2 chip stack and made it into 2 separate ones. So I'm going to get 1 point for it, 1 times 1, and so on, right? So I have 2 more moves, right? And then after 2 more moves, all I have are 7 separate chips, right? So obviously I have no more moves to make, right? Okay, so how many points did I make? 12 plus 4, 16, 18, 19, 20, 21 points, right? So your goal is to maximize your winning, right? So what do you think is a good strategy for playing this game so that you maximize your winnings? Anybody wants to guess?
You take the biggest stack and divide it by 2.
No, I'm sorry. So let's just okay. Because of the way you are saying it, let me clarify. So you start with a single stack, right? That's the initial configuration. And then as you play the game, you will have multiple stacks. Okay, so can you go ahead and answer the question again? Because I want to make sure that there was no misunderstanding before in terms of what the problem is.
Yeah, so in the first step, you divide this 1 stack into 2.
Yeah, how do you divide it? What is the best way you think?
Like as even as possible.
Okay.
So like divide by 2.
So why do you think that's a good strategy?
Um,
I'm not asking you to prove that it is a good strategy. I'm just asking you sort of to explain your thought process, right? So that way people understand why this is a reasonable strategy.
Squares would create the biggest value for it, I think.
Okay, so for instance, if I take the 7 stack and break it into 6 and 1, right, I'll get only 6 points, right?
Mm-hmm.
So uneven, highly skewed split gives me, if I take a stack of n and break it into n minus 1 and 1, I get only n minus 1 points, right? If I divide it into n by 2 and n by 2, then I'll get n squared by 4, right? Which certainly seems like a more points. And that's where you're coming from, right? Good. Anybody else has any other strategies? No? The answer, of course, is always surprising, right? Otherwise, I won't even ask you this question, right? So the answer is that no matter what you do, you get the same number of points in this game. Okay? So so the strategy is totally irrelevant. You can just, mindlessly do whatever you want. And in the end, you will get n times n minus 1 by 2 points. Okay. So this is easy to see when you use the skewed strategy, right? Because you start with n, then you'll go to a stack with n minus 1 and 1. This will net you n minus 1 points. Then in the next step, you will break up this n minus 1 stack in a skewed way, which will mean n minus 2, 1, 1, and this will give you n minus 2 points, and so on. So you can see that over this game, you will get n minus 1 plus n minus 2 all the way to 1, right? Which we already know the formula for adding these up, and that is n minus 1 times n divided by 2, right? So we can easily see that the strategy that always just takes off 1 and makes a new stack with just 1, that is going to earn this n minus 1 times n divided by 2 points. The interesting part is how do you prove that no matter what you do, you get this number of points? And we can use strong induction to prove this. So why don't we take a break at this point and then reconvene at in 20 minutes, like 4:40, and then we will go through this, and then the rest of the some of the homework problems. I'll also answer questions if you have any on the homework 5. Okay. Very good. So let's take a break and come back in 20 minutes. 4:40, right? So I will keep the session on, so you'll just come back to the same session. Okay. Thank you.